Welcome to the BTP AI Best Practices series. In this session, we'll cover knowledge graph-powered retrieval augmented generation and walk through the key design patterns for building explainable business-aligned generative AI solutions on SAP HANA Cloud. We'll walk through practical approaches for using SAP HANA Cloud knowledge graphs to answer complex business questions with accuracy, transparency, and speed. This best practice guide is part of the SAP BTP AI Best Practice Initiative. This session is organized around 4 main topics. We'll begin with a high-level overview, then review prerequisites for implementing the solution. Next, we'll illustrate the process step by step using real-world scenarios. Finally, we'll share resources to help you deepen your understanding and apply these techniques in your own projects. While there are multiple ways of leveraging knowledge graphs for retrieval augmented generation, here we illustrate a significant example of how knowledge graphs fit in an AI query pipeline, using a knowledge graph to enrich a large language model. LLMs prompt for extracting relevant domain information from documents. We explain this scenario in the context of a specific business use case that deals with equipment industry standards. We build on the foundation of the graph-based RAG knowledge graph creation best practice, where we created a knowledge graph, and now we show how to use that knowledge graph to answer practical business questions using a simple and repeatable workflow. Traditional retrieval methods often struggle to deliver precise and reliable query results, particularly when accuracy and context are critical for business decisions. By leveraging knowledge graphs within your query pipeline, you gain structured semantic access via RDF triples and SparkQL queries, allowing your retrieval process to precisely reflect complex business logic and domain relationships. After learning this best practice, you can set up a simple process for finding business facts and documents and matching them with the definitions in your domain. This will improve the accuracy of AI results and help you explain where each answer comes from. In addition to the foundational concepts that we introduced in the graph-based RAG knowledge graph creation best practice, let's first introduce some additional concepts that are critical to understand the remaining sections of this article. Pipeline integration. The process of connecting your knowledge graph to other AI components, like large language models, so you can use facts from the graph as part of a bigger workflow. Pipeline integration allows seamless linking of your knowledge graph to other AI services, significantly enhancing data accuracy for large language models by supplying structured, reliable facts. For example, the knowledge graph gives expected object properties to the large language model before extraction prompt templating. Building a structured prompt that includes terms or properties from your knowledge graph ensures precision and consistency by embedding explicit knowledge graph-driven terminology into your prompts, guiding the model to extract exactly the required information. This lets you control what the large language model looks for when reading documents. Business traceability. The ability to show where every answer comes from by linking large language model outputs back to facts in your knowledge graph. This is important for audits, trust, and organizational accountability. To get started with a knowledge graph query pipeline on SAP BTP, you just need a few key pieces in place. First, set up SAP AI Core with the extended tier. This lets you run and manage AI workflows at scale. Next, you'll need SAP HANA Cloud as your main database. It holds your structured data, RDF triples, and powers your knowledge graph queries. Don't forget SAP AI Launchpad. It's your control center for managing and monitoring all your AI scenarios. Technically, everything happens inside an SAP BTP subaccount. You'll create your HANA Cloud instance with the triple store enabled, set up AI Core for orchestrating pipelines, and subscribe to the Launchpad to tie it all together. Let's look at how all the SAP components come together for knowledge graph-powered retrieval augmented generation on SAP BTP. Users access the app securely via SAP BTP, which handles authentication and permissions right away. Your application logic runs as SAS or Cloud Foundry services inside the BTP sub-account, keeping things modular and easy to manage. The heart of the solution is SAP HANA Cloud. It combines the vector engine for semantic search, the knowledge graph engine for graph queries, and advanced analytics, all connected by SparkQL for structured retrieval. The Generative AI Hub, AI Launchpad, and AI Core orchestrate secure access to both SAP and partner large language models, applying governance, auditability, and access controls. Everything flows through SAP's trusted network, so every generative AI response can be traced to real business data. This approach ensures you can innovate with AI while staying fully aligned to SAP standards for trust, security, and data governance. In the previous best practice, graph-based RAG knowledge graph creation, we have already shown the simplest process of how to extract triples from a document, save them to the HANA Cloud, and then retrieve these triples from the database in a simple way. Let's now use the augmented knowledge to implement more complex scenarios. The pipeline uses a set of well-defined Python functions to handle each stage. These include reading PDFs, identifying relations, filtering based upon business questions, and retrieving matching triples. Each function is independent and reusable, allowing the pipeline to be scaled or modified for different scenarios. For example, extract and store knowledge graph from PDF can be reused across hundreds of equipment specs while asked. Large language model sample enables consistent responses, formatting across large language models. This modular design supports repeatability, and easy integration into SAP BTP workflows. We will now describe two use cases where we leverage the knowledge graph to enhance large language model queries with domain knowledge. The best way to learn something new is to gain practical skills. We have prepared two simple examples for you that demonstrate the principal knowledge graph query pipeline. In this use case, a procurement specialist receives a technical spec for a motor and wants to quickly understand its energy efficiency characteristics. The PDF is parsed and triples are extracted. These include facts like voltage, frequency, efficiency rating, and more. The pipeline identifies which relations are relevant for the question and retrieves only those. Then the selected triples and the question are passed to the large language model, which returns a clear, concise summary. This helps the business user make quick data back and decisions without reading the full document. This example shows how we use a knowledge graph query pipeline to extract relevant information from equipment specification documents. The goal is to enrich large language model responses with facts derived directly from structured triples. First, we extract triples from the PDF and store them in SAP HANA Cloud. Then we identify all relation types available in the knowledge graph. Next, we filter out only those relations relevant to the business question, retrieve the matching triples, and generate a context-aware prompt. Finally, the large language model summarizes the facts into a clear, business-friendly output. Each step is modular and reusable across similar scenarios. The script consists of such simple steps. First, extract triples from PDF document. Second, get all relation types from the knowledge graph. Third, filter relevant relations for the business question. Fourth, retrieve only relevant triples from the knowledge graph. Fifth, prepare the knowledge for the language model. Sixth, extract and summarize relevant facts with the large language model. This slide represents a complete implementation example of how the knowledge graph query pipeline works for a single document. In this case, a procurement expert receives a PDF containing technical specifications for an individual motor. Instead of manually reviewing the document, the pipeline automates the process from extraction to summarization. We start by extracting all relevant technical facts from the document and storing them as RDF triples in SAP HANA Cloud. The result is a structured graph that captures all measurable properties such as voltage, frequency, and efficiency ratings. This gives us an overview of what kinds of data were extracted. We then use a large language model to interpret the business question, in this case, summarize the energy efficiency of this motor, and filter the relations to select only those that are truly relevant to that topic. Once the relevant relations are known, we retrieve just the corresponding triples from the graph. This ensures that only contextually meaningful data is passed to the large language model. Finally, we generate a custom prompt that includes the selected triples and the original business question. This prompt is submitted to the large language model, which returns a concise human-readable summary. Here we show how the final prompt is constructed to answer a specific business question using facts extracted from a knowledge graph. Let's walk through this process. First, the business question is simple. Summarize the energy efficiency of this motor. To answer that, we don't just give the large language model the full document or even the whole graph. We first filter the relevant triples. In this case, these are only the ones that relate to the relation type as efficiency rating. You can see a sample of these triples listed at the bottom of the slide. They describe efficiency values in specific voltage and frequency settings. Next, we prepare the prompt. The prompt template asks the model to act as an equipment expert, provide the filtered technical facts, the triples for summary, and repeats the business question. This structured format ensures the model has only the precise data it needs, clearly framed, and avoids any hallucination or irrelevant content. Finally, the model responds with a concise, business-friendly summary. It captures patterns and efficiency ratings for different voltages and frequencies, all without the user needing to open the PDF or manually compare the values. The result is fast, verifiable, and grounded entirely in facts. In this second business case, we focus on a procurement expert tasked with evaluating whether a new industrial motor, motor B, can reasonably replace an existing motor A. This is a common situation in industrial procurement where decisions must be based on detailed technical specifications that typically are buried in manufacturer PDFs. Key criteria, including power ratings, efficiency, class insulation, and more. Manual comparison is labor-intensive and error-prone. That's why we automate it. Let's walk through the pipeline steps shown in the diagram. Extract the triples from each document. Both PDFs are processed independently to extract technical facts into structured knowledge graphs. The results are graph A and graph B. Get all relation types. We identify all possible relation types in each knowledge graph, such as has efficiency rating, has insulation class, and so on. Then filter relevant relations using the business question. The system selects only those relations that are relevant to the comparison. For example, attributes related to efficiency or power. Then retrieve matching triples. We extract only those facts from both graphs that match the filtered relations. Now build the prompt. The selected triples are formatted into a prompt that contains just the relevant data for the large language model. Run the large language model. The large language model produces a side-by-side summary using only the trusted and filtered facts. By splitting and rejoining the flow like this, we ensure the comparison is accurate, explainable, and reproducible. The user gets a clear answer, grounded in both documents without ever reading them manually. In the first knowledge graph pipeline case, we focus on processing a single document to generate a concise summary using a knowledge graph. Now we extend the same pipeline logic to compare two equipment specifications side by side. This code example shows how the pipeline is adapted to process both documents, one representing motor A and the other representing motor B. We can begin by extracting triples from both PDFs and storing them into two separate graphs, like graph name A and graph name B. Next, we retrieve all relation types and filter only the ones relevant to the business questions. Can motor B replace motor A? In your setup, once the relevant triples are identified from each graph, they are passed into the final prompt. The prompt clearly separates facts from motor A and motor B, and then asks the large language model to generate a comparison and judgment. By the end of this step, we have an automatically generated business-ready comparison based entirely on trusted structured data. This eliminates the need for manual processing and provides a clear answer to whether one motor can substitute the other. Here we see the final step of the pipeline for case 2, preparing and extracting the prompt for the language model using filtered triples from both motors. We start with the business question: can motor B replace motor A in our setup? We then build a prompt that includes two sections, first the relevant facts for motor A, and then the corresponding facts for motor B. These triples were filtered from the respective knowledge graphs based upon the questions. Finally, the large language model is asked to give a practical conclusion on whether motor B can reasonably replace motor A. As shown in the output on the right, the motor gives a clear and structured response. It explains that motor B cannot replace motor A, citing three technical mismatches: power rating, efficiency, and speed rating. This level of explanation is only possible because the prompt is grounded in structured and context-specific data from both documents as well, not generic or assumed knowledge. From a business perspective, this directly supports the role of the purchasing specialist or maintenance engineer responsible for replacing equipment. These specialists often have to compare PDF specifications from different suppliers, which is time-consuming and error-prone. Here, a knowledge graph and large language model approach reduces risk by ensuring that all reasoning is tied to expected explainable facts. This approach saves hours of manually reviewing and comparing each pair of documents. It also minimizes the likelihood of missing a critical incompatibility such as a capacity or rotation rate. It enables standardized decision-making across locations, teams, and vendors. This can be trusted in other areas such as comparing contract legalities, evaluating alternative materials, or checking software dependencies. Anywhere a structured comparison of unstructured documents is required. Ultimately, it is a scalable, auditable process that shifts decision-making from intuitive or ad hoc heuristic analysis to structured, traceable analysis, increasing both confidence and speed. If you want to explore this in more detail, visit the Knowledge Graph RAG Query Pipeline Best Practice page for tutorials and articles showing different aspects of using knowledge graphs. You'll also find additional materials on how knowledge graphs and large language models enable faster, safer, and more explainable business decisions. This best practice guide reflects the collective expertise of AI specialists from across SAP, bringing together insights to support your journey. Thank you for watching this session. We hope the information provided helps you successfully implement advanced generative AI capabilities in your business applications.